Hello everybody, another video on the Ethereum Virtual Machine. In this video we want to have a look inside the Ethereum Virtual Machine during the execution of a smart contract. I hope you had already a look at my other video on the Ethereum Virtual Machine, which gives an introduction to the Ethereum Virtual Machine. For the purpose of this video we want to use the Remix IDE, which you can also have access to at remix.ethereum.org. And for the purpose of this video, we will use the Remix default workspace, which gives us some examples here, some example smart contracts. Here we see an example smart contract, which is very simple. It has only two functions, a store function and a retrieve function. The store function, as the name indicates, stores a value in the smart contract, and the retrieve function gives this value back. On the left-hand side, we have access to the Solidity compiler, which is used to transfer this Solidity code into bytecode, which can then be executed on the Ethereum virtual machine. We just have to click here the compile button and we get the compilation results. When we click here on bytecode, we see here the checked code that can be executed directly on the Ethereum virtual machine, and a slightly higher representation, the opcodes. In order to see what's going on inside the Ethereum virtual machine, we first need to deploy this smart contract. We again go to the left-hand side to the Deploy and Run Transaction tab, and we can simply click here on Deploy, which deploys our smart contract on a simulated Ethereum node. And when we click here onto this little arrow under the deployed contracts, we see here two buttons, one store button and one retrieve button. The store button can be used to form a transaction to store a value within the smart contract, and the retrieve button then forms a transaction that retrieves the value that is stored within the smart contract. So first we want to store a value here, and let's say we want to store the value of 5, and I will click store here, and then we get the corresponding transaction. We can open here some details of the transaction, for example the transaction hash. Here we also get information about the gas that was used. In order to see now what went on inside the Ethereum virtual machine, we click on the debug button here. Then the debugger that is integrated into the Remix IDE is opened. We see the Solidity code on the right side, and on the left side we see some details from within the Ethereum virtual machine. For example, we see the code that is executed within the Ethereum virtual machine. We see the stack, we see the volatile memory, and we see the non-volatile memory. So let's go to the beginning, to the first instruction that is executed when the smart contract is called. It's a push 180 instruction, which pushes the value hexadecimal 80 onto the stack. So if we go over this instruction, we see that we now have the value hexadecimal 80 on the stack. Next, we push the value 40 onto the stack. Then we have an mstore instruction, which uses now these two values on the stack. The value 40 is used as an address to store the value 80 in the memory. So we go over this, and we now see that we have at the storage location hexadecimal 40, we have the value 80. Next, we come to the instruction call value. This pushes the amount of ETH that was sent with the transaction to the stack. We see here this is 0. Then we test whether this is 0. or not. And because it is 0, we jump then to a certain destination here within the program. Then we pop the stack, we push the value 4 onto the stack. Then there is the instruction called data size. This gives basically the size of the data that was sent with the transaction onto the stack. This here is 24. Then we have a lower than instruction here, which basically tests whether 24 is smaller than 4, which is not the case. So we have after this a 0 on the stack. This is done to determine whether the size of the data that is transferred with the transaction is at least 4 bytes long, because 4 bytes is the size of the identifier of a function. So the data needs to be at least minimum 4 bytes long when we do not have an argument that is sent in addition to the name of the function that is called. Okay, now we know that the data that has been sent is the minimum 4 bytes long. In the next step, the program wants to find out which function is actually called. In order to do this, with the instruction called data load, the first part of the call data is pushed onto the stack. You can see it here. This is the first part of the call data, which contains here in the front the identifier of the function that is called. And this first part is now isolated through a shift. And now you can see that we have this first part of the call data here on the stack. And we do a comparison now between this identifier we have sent with this value here, which basically is the retrieve function. So we compare it here, which is not equal. We step further through the program, and as you can see, now we again push another value on the stack, which is now the identifier of the store function. We compare it here. Now it is equal, and then basically we jump to destination, the store function. Yeah, like this, you could now step through the entire program. We want to go now to the store function. Here we see the store instruction. This store instruction now stores the value of 5 in the non-volatile memory. Let's scroll down here a little bit. Here we see the non-volatile memory. When we go over this instruction, we see that we have now the value 5 in the non-volatile memory with the key 0. A store instruction is a very expensive instruction. Here in the step details, you can see the gas amount that is required to store the value in the non-volatile memory. It's expensive because all the Ethereum nodes need to store this value in the storage, and this is the reason why it's rather expensive. If you compare it, for example, with the pop function, it only requires 2 gas, and the store function requires 22,100 gas. This is all for now. I hope you got a good insight into what's happening within the EVM during the execution of a smart contract, and I hope to see you in one of the next videos.